Okay, class, for part 2 of identifying types of chemical reactions, we're going to pick up with our 4th type, the single displacement reaction. How would we define a single displacement reaction? Well, a single displacement reaction can be described this way. An element displaces a like element, and we'll define what that means here in a second, from a compound. To form a new element and new compound. So on the reactant side, if you want to recognize a single displacement reaction, we would see an element often called a lone element because it's off by itself, and a compound. And looking at the definition, we would expect on the product side to see a different lone element and a different compound. We're going to look at several examples of single displacement reactions. These tend to be a little bit trickier than, for example, a combustion reaction, which is always CO2 and H2O. So we'll go over several examples to make sure we get the idea of how to predict the products of a single displacement reaction. In the first example, what if we took zinc metal and reacted it with silver 1 chloride? If you look at the reactant side, you notice that we have a lone element, zinc, all by itself. And we have a compound, silver 1 chloride. It's a classic single displacement reaction. Now, how do these react? Well, the definition says that the lone element displaces the like element from the compound. So what happens here is zinc, all by itself, I like to think of this kind of like a dance partner thing. We have silver, there's dancing there with chloride ion. Zinc, off by himself, decides, oh, I'm going to maybe kind of like you see in the movies when some people are waltzing and someone walks up and taps the dancers on the shoulder and says to the male, the guy dancer, hey, may I cut in? And then, usually if they're being polite, the dance partners change. And then zinc would be then allowed to dance with chloride. That's a good way to think about this here. Now, why would zinc, in this case, try to displace silver and not try to displace chloride? Well, again, we look at the definition. It tries to displace a like element. Well, zinc is a metal. And if zinc is going to try to displace the element from the compound, the element it's going to try to displace is the other metal. And so it's going to have, the way we look at this is zinc will come over and say, basically, oh, I'm going to kick silver out. That's kind of how I often say kick silver out, or being more polite, tap silver on the shoulder and says, may I dance with chloride, please? And then silver says, okay. Well, if that's true and silver is released from its bond with chlorine or chloride ion, predicting the product, well, the first product is fairly easy to predict. To predict the new lone element, you simply have to look at the metal, in this case, that's the element that's being kicked out. And so the formula for our first product would be silver, the element. The formula for silver, Ag. Well, then you have to look at the second product. And again, we have to go back and ask, how would zinc, if it were going to bond to chloride, how would zinc, a metal, bond to chlorine, or it is the chloride ion now, but that is a non-metal. So if we're going to form the product between zinc and chloride, metal to a non-metal, ionic. And so what we need to do is write the ions, and then we do the crisscross. Remember, that was our dance, our crisscross dance. So I would have to write the zinc ion. When zinc forms an ion, zinc forms a 2+ ion. Chloride, a 1- ion. We crisscross those, 2, 1. And what this says is 1 zinc ion will bond to 2 chloride ions, and we would write our formula, ZnCl2. Notice that in our products, we have a different lone element and a new compound. Let's look at a second example. Okay, next example, if we took aluminum, metal, let's be consistent here, we'll do this in blue, aluminum metal plus copper 2 chloride, the formula for copper 2 chloride, CuCl2. Again, we examine our reactant pattern. We have a lone element, aluminum. We have a compound, copper 2 chloride. Aluminum, again, standing by itself, sees copper dancing with chloride, wants to cut in, wanders over and says, can I dance with your date? Okay. Again, aluminum would approach copper because aluminum is a metal, copper is a metal, and that's who's going to want to exchange dance partners. Aluminum will tap copper on the shoulder. Copper lets aluminum cut in, so copper is going to be by itself, the new lone element on the product side. So the formula for our products, first one is the easier one to write. It's just whatever element this is, copper. And then aluminum will bond to chloride. Again, we got to go back to our square one with our chemical bonding idea, or our chemical bonding concepts. Aluminum is a metal, chlorine is a non-metal. How will they bond? Those two are going to bond, form an ionic compound. Go back to, we got to write the ions. What would the aluminum ion be? And then we do our crisscross. Okay, aluminum ion. Aluminum is in group 13. It would form a 3+ ion. Again, these, we've had to memorize our ions. We should know our ions. Chloride, Cl-. Let's crisscross those charges to help us find our subscripts. So what this says is 1 aluminum ion would bond to 3 chloride ions. And the formula that would represent that situation would be AlCl3, aluminum chloride. Okay, so let's summarize. Reactant side, lone element aluminum. Product side, lone element copper. Notice our metal displaced, that's what it looks like, right? Our single lone element aluminum has sort of displaced copper from its bond, and then aluminum is then joined up with copper's dance partner to make aluminum chloride. That's kind of the name, single displacement. You can see that a single element has been displaced from its bond. Now, class, you may be looking at the equation I wrote there and say, well, that's not balanced, Mr. S. You have 2 chlorines on one side and only 3 on the other. Well, again, we could always go and balance this equation using our coefficients as we learned in our balancing chemical reactions section. But we're not going to worry about balancing right now. Let's just get the prediction of products down, because then you would always then, once you predict your products, balance the equation. Let's look at a final single displacement example. In this example, if I reacted magnesium bromide with fluorine, we notice that we have a lone element, fluorine. We have the element F2. This is our lone element, and this lone element is a nonmetal. And this compound, magnesium bromide, that is our compound. How would the single displacement reaction occur? Well, since fluorine's a nonmetal, it will approach bromine, the other nonmetal, and look to cut in. So in that case, the element that's being displaced is bromine. So the formula for bromine, the element, bromine is one of our Brinkelhoff elements that we've talked about earlier. Those elements that in an elemental form are diatomic. So bromine then would be the element that would be displaced. And so I would write the formula for bromine, and then that would mean that magnesium and fluorine would bond. So nonmetal displaces nonmetal, and then magnesium would bond to fluorine. And how those would bond? Well, magnesium is a metal. Fluorine is a nonmetal. You got it. We write the ions, and we'll do our crisscross. The magnesium ion is Mg, 2+, and the fluoride ion is F-, crisscross. 1 magnesium bonds to 2 fluoride, and we would get a product of MgF2. So again, we have a lone element displacing the like element. Metals in single displacement reactions, metals displace metals. Non-metal lone element will displace the non-metal that's already bonded in the compound. Okay, class, let's look at our last type, double displacement. No, not baseball. Get out of there. It's double displacement, not our national pastime. Okay, he's getting out of here. We're getting back to double displacement. There we go, double displacement. In a double displacement reaction, 2 compounds on the reactant side react to form 2 new compounds from an apparent swap of ions. We'll see how this happens on our example. So on the reactant side, usually we're going to see 2 compounds. Very often those compounds are ionic, but they don't have to be. And then on the product side, we will form 2 new compounds by a rearrangement of the members of the original reactants. Let's get right to our example. If we took potassium hydroxide, I'll get it right, plus barium chloride, we see we have 2 compounds apparently ionic. And what they would do, it was they would look like they would swap ions. So what's going to happen here is that potassium sees barium dancing with chloride, and potassium would rather dance with chloride, and barium sees hydroxide and would rather dance with hydroxide. And so kind of like in a square dance arrangement, instead of a waltz, as we talked about with single displacement, these guys will swap dance partners. That's the way I look at it. If barium bonds to hydroxide, that would be an ionic compound. You would write the ions and do the crisscross. Potassium would bond to chloride. Write the ions, do the crisscross. So class, I've written the 2 ions and I've done the crisscross.